In this video, we're going to look at the relationship between the domain and the range of a function and its inverse. And we're going to start with more of a graphical and a table approach to see these relationships that take place. A couple of terms for us to define here first is the word relation represents an expression that relates any x and y together. A function is a relation where every x value is assigned to a unique y value, and graphically functions will pass the vertical line test. An inverse works in the opposite direction, so it will take the outputs of a function, so the y values, and it will map them back to the original inputs for the function. So it takes a y and maps it back to an x. Now let's look at this table for the function y equals x squared, which is right over here on the left-hand side. And I have some x values pre-selected for us to fill in. So I want to fill in the table to get the outputs for the function x squared for all 7 of those x values given. So it'd be 9, 4, 1, 0, 1, 4, and 9. And I want to graph those points as well. All right, now that I have the points graphed on the right-hand side, we can see the graph of y equals x squared. Now I want to go through the process of finding the values of the associated inverse relation. Now, algebraically, when we're finding the inverse, you want to swap the x's and the y's. And the same thing will happen with from a table approach, or even graphically, we would just turn coordinates around. So from a table, the original x values that were listed from -3 to +3 are going to become the outputs of this inverse relation. And what's going to also happen is the y values are going to become the x values for this inverse relation. So 9, 4, 1, 0, 1, 4, 9 become the x's. And we're going to turn right around and we're going to plot those points. Okay, so now we have the graph of the inverse function, and we look at the two graphs, and there does exist some symmetry between the two curves. And in fact, the symmetry between the two curves is about the line y equals x. And I'm going to graph that because it's a little hard to see because the scale of this graph isn't squared. My grids are more rectangles. So now I have the line y equals x on this graph, and we can see if we folded the purple graph over top of that red graph, it would lay on the green. And so that is the kind of symmetry that exists between a function and its inverse. They're symmetric about the line y equals x. Now, another thing for us to keep in mind here is let's look and compare the two graphs between y equals x squared and this inverse relation in terms of the domain and the range. Let's look and let's compare the domain and the range for the two functions we have drawn, and more specifically, the table of values in the graph that's given. So if I'm looking here at the table of values, and the domain for f of x equals x squared is from -3 to +3. And the range for f of x goes from 0 to 9. If I do the same thing for the inverse function, which was in green, the domain of the inverse function, so the numbers that we were putting into the green graph, which I guess is the x column, goes from 0 to 9. And if I'm looking at that green graph, scanning from left to right for the domain, the farthest to the left that it does go is 0, and it goes all the way to 9 in terms of as far as we plot it. Now, the range, or the outputs of this function, just from the table that we have, goes from -3 to +3. So notice what is happening here in this table, how the domain of the regular function became the range of the inverse, and likewise the range of f of x became the domain of the inverse, how they flip-flop there. Now let's repeat the steps and do it for a new function here. We have the function y equals 2 to the x power, and I have a table pre-made. It's the same x values as the previous problem. We're going from -3 to +3 for f of x equals 2 to the x power, and we'll get us some outputs here. And we'll fill in the tables. And now we just want to plot that onto our graph. All right, so now we have the graph of y equals 2 to the x plotted to the right there in purple. And now I want to go through and fill in a inverse relation table from the table we have for y equals 2 to the x. And remember what happens. We swap our x's and our y's. So the x's for f of x become the y's for my inverse relation, and the y's for f of x become the x's. And then we're going to graph. All right, so now I have the graph of the inverse relation there in green. I actually went ahead and plotted the diagonal line y equals x, and we see that there is the symmetry between the f of x and the inverse relation. They're symmetric about that diagonal line y equals x. Now let's go into the table and let's write the domain and the range for both of these functions right here below so we can see the relationship that exists. So the domain for f, which is the purple graph, in terms of what we plotted, goes from -3 to +3. The range of the f function, in terms of what we plotted, goes from 1/8 to 8. Now I want to do the same thing for the inverse function of what we plotted. So the domain for the inverse, the green graph, goes from 1/8 to +8. And the range, or the outputs, of this inverse function will go from -3 to +3. And if you look at the relationship that exists between the domain of the function and the range of the inverse, how that domain of the function of x became the range of the inverse, and likewise the range of f of x is the same as the domain of the inverse function. Okay, so now we want to use that relationship to help us find the range of a function without actually having a graph to look at or using a calculator. And so that relationship where the range of f of x is equivalent to the domain of the inverse function is going to become very useful for us in order to do this. Now there is something to keep in mind, is we have to be very careful when we're applying this relationship, because at times if you proceed too far in your rewrite for the inverse equation, you can accidentally remove some restrictions of the original function when it comes to finding out this domain of the inverse. And so we just have to do a quick double check at the end to make sure we didn't miss anything important. So I want to start off by to find the range, we need to first find the inverse. So I'm going to go through the process and swap my x's and y's and do the rewrite. And then I would need to multiply the denominator over. And for this one, we would have to distribute the x. And then get our y's on the same side. And move the 3x to the other side. So it'd be xy minus y equals 3x. Factor out a y. And divide by x minus 1. And so we have our inverse. So I want to start by finding the domain of the inverse function here. And we're looking at the function y equals 3x over x minus 1. Well, the domain of this inverse function is basically going to be the values of x that you can put in and have a defined value. Well, what we do know is that we cannot use x equals 1, and we can use any other number outside of that. So that domain here is going to be from -infinity to 1, and then 1 to infinity. There's no other restrictions in the domain of the inverse, so what that means is that becomes the range of f of x. Okay, now let's look at another. We want to do the same thing. We want to determine the range of f by using our inverse function. So we got to start off by trying to find the inverse function. Now what we're going to have to do with this kind of problem is we're going to look at the right-hand side here, and we're going to see that that is a perfect square, so we're going to need to factor it. That makes y plus 3 squared. When it comes to finding out domains and ranges, all right, this here could be an important line for us to revisit down the road. But for right now, let's go ahead and continue the process of rewriting this thing as y equals. So I would take the square root of both sides, and remember, when you take the square root of a square, you have to account for two possible outputs, and we create the absolute value of what was on the inside. So square root x is equal to the absolute value of y plus 3. When I take off the absolute value, I end up with positive negative square root of x. Could be equal to y plus 3. And so we get our inverse equation to be 3 plus or minus the square root of x. And so we would have to figure out, if we were going to do some domain restrictions of f, so that way our inverse would also be a function itself. We would have to figure out if we were going to use the positive or the negative one. But regardless, in context of this, we're going to find the domain of the inverse. I look at that square root function. The smallest number that I can put inside of the square root and get a real number output is 0. So the domain here, 0 to infinity. Which means that if I go back and I look at the original problem for f of x, that domain for f, or excuse me, that domain for the inverse of f should be the same as the range of f of x. Now, I could have also determined that by looking at the line that I have the arrow beside. Because if you look at where x is set equal to something being raised to the second power. And we are working with all real number outputs here, so I would know that the smallest output I get by squaring a number would be 0. So I could have jumped right in and determined my domain and range from that line right there. Do another one here. So I need to start off. I want to find the range of f of x. And I could look at this problem and say, well, it's the square root, so we would think that the smallest output of the square root would be 0 and go up to infinity. But let's confirm that through this process of finding the inverse. So I swap my x's and y's here, and I go through the process of trying to rewrite. And if I'm going to write this thing as y equals, the next move that I would do would be to square both sides. And then I would add the 1 over and take the square root. And remember, the square root of a perfect square creates the absolute value. It'd be the absolute value of y, and then I would need to pick. And so our inverse function here is going to be it's going to be equal to positive or negative square root of x squared plus 1. So I want to look and I want to determine what the domain of this inverse would be. Well, we're looking at this inverse function with the way we're written, and because the inside is x squared plus 1, what I can do is I can put in any number I want to in for x, and I can get a real number output. And so the domain for f, or the inverse of f, is equal to all real numbers, which would make us think that, well, wait a minute now, so does that mean the range of f is all real numbers? And the answer to that question is absolutely no. The reason is because back here in that original line, when we went through and continued the rewrite to try to get this problem to be y equals, we removed a restriction when we took off that square root right there. Now, from this part in purple, we would look at where the x is located and say, yeah, I could put in any number I wanted to for x, but for x and y to make sense, I should know that based on that equation for x, I could only really have values of x that are 0 and larger. And so this is example of a problem where you would have to be careful. So the actual domain, when I don't have the restriction, when I don't remove the restrictions to get it to be y equals, is actually going to be from 0 to infinity, which means that that's going to be the range of f. So we have to be careful if we just make a habit of jumping in and writing everything as y equals and then finding out our domain. It's almost better to do it right after you swap your x's and y's, if you could tell right then and there without doing a rewrite. All right, now let's try to find the domain for some function operations. And I have a little table here to summarize how to determine this domain based on the operations. However, it's often easier to kind of do this as we go. Now, the examples that I have are mainly for the quotients and the composition of functions, because those are the ones that are the more difficult ones to see. The products and the sum and difference are ones that, if you know what the domain of f and the domain of g are separately, you look for the terms that fall in both of their domains, and that'll be the domain for the operation. So I'm looking here at this first problem. I want to find out what g divided by f of x is, and then determine the domain. So g is the square root of 3. F is the square root of 5 minus x. And so in order to do this, what you're going to do is you're going to look for the domain when you don't have your problems simplified. So I just laid them into the operation where they belong. And then now I'm going to look at the domains individually. So the domain of the purple equation, so the square root of x minus 3, that domain goes from 3 to infinity. Keeps what's up underneath the radical 0 or larger. The domain for the denominator goes from, the biggest number you could put in would be 5, but I could not include 5 because that would make me have division by 0, and I could have as small of a number as I wanted. So the domain for the operation is going to be the overlap in those two domains, which would basically go from 3 to 5. That's the overlap region. Now, in terms of simplifying this problem, you could simplify it by, if I had the quotient of two radicals, I could make it the radical of the quotient. All right, let's look at this. We want to have f divided by g of x. Now, looking here at this problem, and I already have it laid out, is we want to put the functions in where they belong and then determine their domains respectively. So let's start with the denominator's domain. So the square root of 8 minus x here. The domain, the largest number that I could put in there would be 8. However, because that would make me take the square root of 0. However, because this function is in the denominator, I cannot use 8 because that would create division by 0, so I'd have to exclude it. There is no limit to how small of a number I could use, so I'd go from negative infinity to 8. In my numerator, I'd have the domain. The smallest number I could put in would be 3, and I can use that because I can have 0 in the numerator of a function, and there's no limit to how large of a value you can use. So there's the domain for each individual part. Now, the overall domain for the operation is going to be the overlap in those two regions, which, looking at it, would go from 3 to 8. And to simplify this problem, I could rewrite it as one radical. All right, here we're looking at the composition of functions, and we're using the composition O to represent that. And I could rewrite this as f of g of x. So f parenthesis and then g of x here, like that. Then you can see exactly what goes where. Now, since I want to determine the domain for this operation, I'm going to perform the composition, but I'm not going to simplify it right out of the gate. So as soon as I do the operation, now is when we do the domain. Because f, I am squaring f, or squaring the x in f, I can put in any number I want to. However, if I'm looking at g, because g goes inside of f first, there is a limit there in terms of this, what kind of numbers I can use. They have to be 0 or larger. So my overall operation domain goes from 0 to infinity. So I do it right then and there. And then you could go on and simplify. So the simplified version of this problem would be 2x plus 1. Now, if I would have waited until I simplified, I would have said that the domain would have been negative infinity to positive infinity, which would be wrong, because I actually have to square root the number before I square the number. All right, let's look at one more composition of functions. So I want to find g of f of x. I'm going to take the square root of x plus 2, but instead of writing x, I'm going to put f in its place. So x squared minus 4. And for this one, I am going to go ahead and put the negative 4 and the 2 together. And so I'd have the square root of x squared minus 2 up underneath the radical. And so now I want to find the domain for that operation. Well, everything's up underneath the square root, so the smallest number that I can take the square root of is 0. So I want to find the zeros of x squared. So x squared minus 2 is equal to 0. X squared is equal to 2. I take the square root of both sides. I get the absolute value of x is equal to the square root of 2, which means that I have two numbers, positive or negative the square root of 2. Now, the way we can determine what we can use is I can make a little number line here, and I can put those zeros on the number line and do a little sign test. So I'm going to test around those numbers to figure out when is x squared minus 2 bigger or smaller than 0. Well, let's start by picking a number less than negative square root of 2. So let's say I picked negative 3. If I put negative 3 inside where the x is, so if I put negative 3 in here, I squared it, that gives me 9. 9 minus 2 is 7. That is bigger than 0, so check, that works. Now let's pick a number that lies in between positive and negative square root of 2, like 0. If I put in 0 for x, I square it, that makes 0. Minus 2 is negative 2. I can't take the square root of negative and be real, so I can't do in between those two values. And lastly, pick a number bigger than the square root of 2, like 3. Positive 3, square 3 makes 9, minus 2 is 7. That's bigger than 0, so that works. The domain for my operation is going to be where all the check marks are. So the domain for the operation, in this case, would be from negative infinity to negative square root of 2. I include that. And then I would have to join it with the union and go from the square root of 2 to infinity. So there's my operation domain.